Welcome to the Nanovation Podcast. Information about this and other episodes can be found at fillerlab.com/nanovation. If you like what you hear, be sure to tell a friend or leave a review at Apple Podcasts. It really does help. I welcome your thoughts and suggestions. You can contact me on Twitter at Michael Filler or via email at nanovationpodcast@gmail.com. Thank you to the Chi Foundation for their generous financial support.
These separation processes are complicated, and currently the only way around it is, if you don't want to think about separation, is that you have to make the perfect product to begin with, or you just accept that whatever you have is what you're going to have to live with. And I think adding separations to your arsenal of techniques, a range of separation techniques, allows you to be a little bit sloppier in your synthesis, or if you have a not so great product, to upgrade what you can use the product for by using the different separation techniques.
That's Victor Breedveld, a professor of chemical engineering at Georgia Tech. In that clip, he's talking about the need for separations or purification steps in future nanomanufacturing processes. In this episode of Nanovation, Victor and I discuss a perspective article titled Process Principles for Large-Scale Nanomanufacturing that we co-authored with our colleague Sven Behrens and graduate student Maritza Mujica. We overview the state of the art in terms of nanomanufacturing. We talk about the pros and cons of modular versus integrated manufacturing paradigms. We talk about why we think the chemicals industry is a good model for a future nanomanufacturing industry. We discuss the physical phenomena that complicate the processing of nanoparts, and we end with a discussion of the science and engineering required before the real potential of nanotechnology will be felt by the average person. We cover a lot of ground in this episode, but somebody's got to do it. This is the Nanovation Podcast, an exploration of big innovations emerging from small things. I'm Mike Filler, your host and a professor at the Georgia Institute of Technology. Enjoy the show. It is my pleasure to have Victor Breedveld. He is an associate professor and the Frank Dennis Faculty Fellow in Chemical Engineering here at Georgia Tech, so welcome.
Thank you.
I've known Victor for coming up on 10 years, which is kind of mind-boggling, ever since I joined the department as an assistant professor, and he and I have been talking about research ideas pretty much since then, and Victor's one of my favorite people in the department to chat about technical things with, and pretty much anything else. He's sharp as a tack, and this is actually one of the things that blows my mind is he is an avid runner and pretty much still runs actively to this day, and yet no matter how much he runs, he still is sharp. I find that if I run too much mentally, I just go off a cliff.
For me, it goes the other way around. If I don't run enough, I start going off the cliff. It's my way to stay mentally healthy.
Okay, but is there an optimum? Because I agree with you that there is a certain region where I need to be doing it a little, and if I do too much, like I'm training for a half marathon, then and I'm running 4 or 5 times a week, then I can go off the cliff.
My optimum is probably shifted a little bit from yours. It's true. For a marathon, I don't have time anymore.
Right.
But for a half, 10Ks, 4 or 5 times a week is not a real problem. That's actually where I'm probably best.
Okay, right. And that's where I'm probably worst. So he's also the associate chair for undergraduate studies in the School of Chemical Engineering. And if we have a chance, we'll talk a little bit about that in the end of the show. He got his MS and PhD from the University of Twente in the Netherlands, and he's from the Netherlands originally. And your degree was in what discipline?
In applied physics. My research area was complex fluids, colloidal materials, and if you would translate it here to the US, it would most likely be in a chemical engineering department.
So what about it makes it chemi versus physics?
The kind of materials and processes would here be discussed in a chemical engineering department. If I look at my colleagues from when I was a grad student who were in the US, they were almost all affiliated with chemical engineering departments. Chemical engineering in Europe is more chemistry oriented generally, so it would be more chemical technology. Here, chemical engineering is very math heavy and therefore closer to maybe an applied physics in a lot of areas, especially if you combine it with chemistry.
Okay. I didn't realize I was such an applied physicist. I'll tell people that. You don't know this, but I'm basically an applied physicist. Okay, very cool. And so why don't you take a second to describe the focus of your group's research?
My group's research is really focused on two directions right now. The first theme is how do I control the microstructure of complex fluids, materials that are neither simple fluids nor solids, anything that's gooey. If you poke at it, it will move. If you let it sit, it will ultimately flow. How do you control the mechanical properties by controlling the ingredients? Classic examples that everybody can associate with is paint, for example. If you ask yourself, how does a good paint work? You all know what a good paint is, but you don't realize how crazy the requirements are. You want something that is thick enough that over time the pigment particles don't sediment when it's sitting on the shelf between you purchasing it and finally being nagged by your wife to put it on the wall. At the same time, when you open up the can and you put it on the brush, you want it to be thin so that it can easily, without too much effort, be applied to the wall. And then you want it to thicken quickly again, because by the time you take the brush off the wall, you don't want it to drip anymore, but it has to thicken at exactly the right time scale so that surface tension has the ability to smoothen out the surface so that you can get the brush strokes. People never think about what makes a good paint, but you know it when you see it. And there's a lot of engineering of structure and interactions behind it.
I won't be so mad the next time I go into a Sherwin-Williams and they want to charge me $75 for 1 gallon of paint. It sounds more advanced than most people appreciate.
It definitely has evolved dramatically over the last couple of decades in what is in there in terms of design. So yeah, is it worth the $75? That's a good question, but it's definitely, you get good technical value for money.
We were speaking of whether it's worth the money. I have 2 rooms in my house that have been painted that I painted with nice quality paint, the kids' rooms. And we were talking about the kids earlier. They can rub dirt up on the wall, and a good quality paint, you can wipe it off, right, without the paint coming off the wall at the same time. A bad quality paint, one that you may pay $20 a gallon for, you're taking the paint off the wall at the same time. So in many situations, it's really great to pay $70 for the paint.
When it comes from a company that really has paid attention to those details, it's amazing what you can get. So that's the first part of my research, and it's not that I do paint research, but it's a good example to talk about. The other part of my research focuses on wetting of porous materials. Can I make paper reject oil, water, one and not the other? Can I use it for filter applications?
So hold up, with the paper example, I'm not sure everyone realizes how porous paper is. Can you describe it real quick?
Porous, quite porous. The material that you buy for your copy paper has a lot of inorganic materials in the top layer so that it controls the porosity, but it's typically about 50% air inside a paper sheet. So that's why it soaks up so much water when you take a paper towel and you try to clean up a spill.
And just to be clear, the bulk of the paper are cellulose fibers.
Cellulose fibers make up the material, and the space between those fibers is what you would call the pore space.
Right, okay. And then for certain types of paper, like printer paper, and there's all sorts of different advanced papers, there's coatings and things on the top.
Yeah, and you really need to control the speed at which liquids enter the paper. If you think about inkjet printing, for example, if you take a paper towel and you try to inkjet print on it, it looks horrible because the liquid gets in too quickly, too easily, and different pixels, different droplets that are deposited really flow into each other, and it doesn't work at all. On the other hand, if you take something that's absolutely non-absorbent, a plastic sheet, now you have the problem that it doesn't dry. So you really try to find the optimum intermediate between those two, porous enough for liquid to enter, but not wetting enough that things start flowing into each other. So that's good science behind that as well. Designing, for example, photo paper for inkjet printing is not a trivial task at all.
One of the things where we've had a conversation before about paper and paper manufacturing has been, and this will lead us maybe into the main topic I wanted to have you on the show for, is in the scale of paper manufacturing, specifically relative to electronics manufacturing, where if you took all of electronics produced with conventional wafer-based technologies and added them up on a yearly basis, it'd be something like 3 miles squared. But if you look at paper, and even just printer paper, and there's, of course, many, many products beyond printer paper that use paper, drywall, etc., it's about 5 orders of magnitude larger per year. And so there's lots of talk about wanting to take nanotechnology, nanoscience from the lab and into these kinds of manufacturing settings and hopefully add functionality to paper, whether it's electronics or some other kind of property. And there's an enormous disconnect between the scale of paper manufacturing, for this example, and other examples where we control products with nanoscale precision like electronics.
Yeah, I think for an engineer thinking about manufacturing, it would be tremendously helpful if you have a visit to both, on the one side, maybe an Intel-like facility and a paper-making facility. It is mind-boggling the speed at which these paper machines operate. It's thousands of feet per minute, typically about 15 to 20 foot wide, coming off the paper machine. And it is still controlled to a very, very high degree of precision, because any kind of defect will lead to rupture on these machines where these large rolls of paper are being spun around and being produced. So it has to be almost perfect. They have to have nano-level control over where everything goes and how it's distributed. But it's a very different production environment from Intel.
Right, as are most things. I think Intel's probably the odd man out in this situation.
The two extremes here. I think also the paper is an odd man out, that there are very few materials that are being produced at that scale. If you go to a plant where they may create plastic sheets, they don't match the kind of production volume of a paper plant. So that's why I say that for anybody interested in manufacturing, seeing both those extremes will make you appreciate both, actually, because you realize that what you would call a low-tech application is not that low-tech. A paper machine costs $1 billion. It takes up a lot more space than a fab for IC production, but the cost level is not all that different. I mean, I think you talk to people in the IC industry, what a fab facility costs for them, it's multiple billions. But a paper machine also is $1 billion.
I didn't realize they were so expensive. But yeah, a state-of-the-art fab, and not all fabs are state-of-the-art, but a state-of-the-art fab is about $10 billion.
Yep.
Okay, so I wanted to have you on the podcast to talk specifically about a perspective article you and I wrote with our colleague Sven Behrens and one of our students, Maritza Mujica. And it appeared in the annual reviews of Chemical and Biomolecular Engineering last year, and it's titled Process Principles for Large-Scale Nanomanufacturing. Can you talk about what a review or perspective article is first, for those who don't know?
In the old days, when nobody had really that much access to a large set of journals, easy access, a review would literally often be a summary of existing literature. Definitely things have shifted, and now a good review perspective article is not just summarizing what's out in the literature, but also trying to interpret it and providing some view and some vision of where the field maybe will go and should go and what the challenges are. And I think our article definitely is in that category. A little bit more provocative in looking at nanoscale manufacturing, nanomanufacturing from a perspective that is just as applicable to maybe someone interested in paper manufacturing. How can you make things work at a scale that practically matters?
Right, and I think you're right to say we were a wee bit provocative. Review articles don't have to have at least as much of a component of the author's thinking, but at some level, every article does, right? You're making choices about what things you reference and what things you discuss, and by definition, you're doing that. But we were pretty clear in our desire to lay out the challenges and lay out where the holes are in our capabilities. Right. So why don't we start by talking about large-scale nanomanufacturing? And I think it's obvious from the first part of this discussion that we are very interested in applying nanoscale materials and devices in very large-scale settings. And those may not be paper, although paper is an interesting example. They might not be as large-scale as that, but it could be window scale, which is 3 orders of magnitude more area per year than electronics, but 2 orders of magnitude less than paper.
Yeah, and I think that's where you really need to appreciate how much is needed in terms of material to fulfill a technical, either current or future need that may arise. I always liked your example that you bring up about how many quantum dots are necessary for the LED, the QLED screens, right? You've quoted a number of what an annual production should be to basically meet all the TV production capability. And that number wasn't too high. That was not many train cars full of nanodots, because they're applied in such a thin layer, relatively small amounts per surface area, and the number of TVs is not that large compared to some other products.
The TV example is an interesting one. I regularly have conversations with people who say, well, but look at TVs. Those are enormous areas. And it's more area than electronics by about 2 orders of magnitude, or an order of magnitude and a half. But it's nowhere near the surface area of, say, all the solar cells produced, or going back to Windows. I mean, your orders of magnitude too low still. So that's an issue. I don't think people realize that sometimes.
No, I think that's a very important statement. You have to define sort of what you're interested in. I think you think about solar cells, that sets a realistic target level. If you think about other materials, and people are thinking about thermoelectrics, for example, and how you could develop devices that would recover some of the heat as electricity in applications like car engines, then you quickly end up with another order of magnitude in terms of the amount of material you would need. And that's where it really becomes relevant that it doesn't just work in your lab, but that it works in a plant, in an environment that is really, really different from your lab. You could argue that you can scale by parallelization maybe the quantum dot production that is necessary for TVs, but you cannot generate enough, for example, nanowires to meet the demand for solar cell or thermoelectric production.
Right. That's exactly right. And it's what we'll talk about today are things where it's not just making more stuff. You have to make it in such a way as to be cost efficient, and there's a lot of fundamental science that's required to do that, particularly in nanomanufacturing. And so that was kind of the point of this article, is to point out these holes and point out what kinds of scientific advances would be necessary, so that people start to say, oh, this is something I should think about and maybe work on, right? So we start the article by kind of laying this out, talking about how our interest is in kilogram and ton scale applications, and Victor was just describing this. And we go in and start describing the difference between modular and integrated manufacturing paradigms. And we're a little bit pedantic and a little bit simplistic, but we felt it was really important to make sure everyone understands the spectrum of manufacturing paradigms. Can you talk about those two and the spectrum between them?
Yeah, so if you think about the way you generate products and you do it effectively. When you are interested in producing cars or PCs, you really want to do it in a modular fashion. You're not going to have a plant where on the one end the iron ore enters and on the other end the car leaves the system.
Although that's been tried. Yeah.
There is a reason why it doesn't exist
Yeah, that's
anymore.
right. It was tried.
Instead, you now have really a production system where the car manufacturer who sells their car buys a bunch of different modules from other suppliers, or they make them themselves in separate plants. And these modules are consistent, again, of smaller modules. And ultimately, you go to the raw materials. It's a very successful model as long as you can define those modules in a way that you can use them for multiple products. It would be very annoying if every car model that's produced would need different tires, for example. Very simplistic example. So they try to define the types of tires in a certain number of classes that are then applicable to all the cars that you would want to produce. That's why the tires for these massive tractors that they use in mining industry, for example, are ridiculously expensive. They only make a few of those. It's not a standardized product, and therefore you end up paying ridiculous amounts of money for a single tire, even though the amount of rubber that's in the tire would not justify that. You just have a production process that is no longer generic enough, no longer modular enough to reduce the cost.
So we do this in computers too. I think computers are a good example where you buy a laptop and up and down the stack, effectively, it's modular. The screen is, like if you're Apple, you might modify the screen, but you generally buy the screen from Samsung. You buy the keyboard, you buy the chips, right? Someone's making the chips, and even the precursors for those chips are modularized, right?
Mm-hmm.
You buy some of the dopant from, pick your favorite chemical company that sells things to that industry, and it's all the way down the stack. And that modularity generally provides cost efficiency when it can be done.
Yep.
And so sometimes it can't be done. And sometimes with products that ultimately become modularized, they are an integrated solution in the beginning before people figure out how to modularize them.
And I think medicine is a good example of that. People wanting to make these very complicated proteins therapies, they right now really have to go in and develop a single specific solution for a specific molecule. But ultimately, you know that these industries would like to be able to mix and match, to have, I need this part of this protein to really make the drug work. I need this part of that protein to get it to the right cells. I need this part to just make it soluble under the environment where I want it to be soluble, either in the stomach or in the gut or even in your mouth. But right now, have not reached that stage for example, something like drugs.
Right. The other thing about modularity that we will talk about, and I think it's a good time to bring up, is that because there are breakpoints between modules, you can separate, right? So you're a module manufacturer. So you're Samsung and you're making the screen. Well, if you mess up, the whole laptop that Apple's trying to build is not thrown out, right? Apple gets good screens because you've tested the screens that work and only sent them the good screens. In an integrated process, there's no opportunity to do that kind of separation or sorting at at as many intermediate stages, and that can also drive up cost.
It's tremendous issue, because imagine that you buy a car and there was one faulty wheel bolt in the system and they have to throw the entire car out. You really want to test those bolts independently to make that happen. But it's not always feasible. There are still industries, and the integrated circuit industry is the biggest example of that, where it's so hard to do the intermediate testing that they just accept that they're just going to have to do all these steps and in the end evaluate the end product and see what works. And it has ridiculous requirements now on the success rate of each individual step, of course, because you have no opportunity to select the, let's say, 1% of failed products at each intermediate step, because that drives it down very, very rapidly. I mean, the simple calculation is if you make 10 steps where each of the steps is 99% certain, the overall process is only 90% certain. And that becomes quickly a liability issue if it's many more than 10 steps.
And in the semiconductor industry, there are hundreds of steps. And the other thing I was going to say about chips is I think it's a little less the testing and more the ability to actually remove anything, right? So all these chips are built on wafers, and one wafer, let's say, has 200 chips. You can't just go and pluck out that one and stop processing it. It's stuck on there, right? So having to continue processing the rest of the wafer for the chips that are still working and are not defective, that one's just stuck.
But it has to do with the cost of testing, essentially, right? Because you would have to remove it from a process, keep it under an atmosphere that's good for it, be able to place it back exactly the way you picked it off, and it's just not worth it. They can't technically easily do that. And building in situ test equipment is also prohibitively expensive. So you make the trade-off, and it's better in that case to just rely on insanely reliable individual process steps, and it has worked. The IC industry made this into an art. They are really, really, really good at what they're doing in each individual step.
So now we've laid out kind of the spectrum of manufacturing paradigms, and there's some on either side of the spectrum. There's some in the middle that have components of integration, have components of modularity. We specifically want to talk about chemicals manufacturing, and this topic has come up time and time again. Surprise, I'm a chemical engineer. I know chemical engineers, so it's a topic that's evergreen on the podcast. But there's a couple points that Victor and I want to talk about how chemicals are processed. And so we're going to do that briefly, and then we'll move into why nanomaterials are difficult to work with and what we see are some of the real opportunities to advance the science of nanomanufacturing. So I think the first thing about chemicals manufacturing is that it is a very modular manufacturing paradigm. We have a sequence of steps where we synthesize a species and then we purify. And by purifying those species and taking a purified product into another step or selling it to somebody else who's going to do something with it, you have this inherent modularity, which is really central to the success of the chemicals supply chain.
And the chemical manufacturing process is really not that good at each individual step. And that's why you have to have this process of running a process, then separating out the bad stuff, taking the good stuff that you wanted and processing that further in a modular fashion. Because where the IC industry would talk about 99.99%, as a chemical engineer, you will never have 99.99% selectivity or yield. There's always some other stuff that ends up in your reactor that is just inevitable.
Right, so that's a good point. So there's a couple reasons why that happens, right? And so in these synthesis steps, it can be something like kinetics, right, where you make not just what you want, but you make a whole bunch of other things that you don't necessarily want. Or you make a bunch of stuff that you want, but they're all mixed together, right, like we get in petroleum refining. And you got to break them apart and separate them and send the gas to those folks and send the jet fuel to those folks or what have you. So that's one of the things. Sometimes in any of those situations, you're limited by thermodynamics.
Yep.
Right. You might want to have 100% conversion, but you don't.
Yeah, and on top of that, when you go to small length scales, and this applies to both molecules and to nanomanufacturing, chance starts playing a role. The thermodynamic driving force kT, which is 10 to the minus 20 joules, give or take, is not going to affect how a wheel ends up on a car. But it is going to affect how self-assembly works on a molecular level, how two molecules that you want to come apart are going to come apart or come together and come apart again after the reaction and all these steps. By going to that level, you inherently subject yourself to chance.
Yeah, let's come back to that in a second. This is a really important point. The last thing I did want to say about chemicals manufacturing is that it works. So with all of this chance, as Victor was describing, and as I was saying earlier, products that are mixtures of things, some of which you want or don't want, chemical engineers make things at massive scales very cost effectively and with tremendous energy efficiency in many cases. So we chose it. Again, we're chemical engineers, but we also felt it was a really valuable industry to make comparisons to nanomanufacturing. Assuming in nanomanufacturing, we're not going to make things perfect like we can in the semiconductor industry. And if we're going to assume that, what are the other things that are required to effectively take an imperfect product and make it perfect? Right.
Or at least let the imperfections not become progressively worse and worse and worse.
Agreed. Yeah, exactly. Okay, so Victor started with this point about what makes nanoparts, we'll call them nanoparts, challenging to work with. And you were talking about stochasticity, basically. There were other things that we mentioned that I think are worth talking about. But maybe let's stick here for a second, right? At the macro scale, when we can hold something in our hands, we have very deterministic handling. We can put a key exactly where we want it. At the molecular and also at the nanoscale, things are different.
Yeah, people use always the term self-assembly as if something magic, right? I put some ingredients in a beaker, I heat it up or do something else to it, and all of a sudden they will come in together in perfect ways. I end up exactly with the same end products, everything looks the same, but it's just not the case. You have a distribution of how the assembly will look like that's governed by the chemical products, but it's certainly not perfect. It's not deterministic, and you have to accept that.
So when you go down to the nanoscale, things like thermal motion become really important. You don't have a key in your hand moving in your hand because of thermal energy. Thermal energy at room temperature is way too low for that. But at the nanoscale and also at the molecular scale, thermal energy can contribute to the random motions of an object.
Yeah, the idea of self-assembly is that everything is moving around randomly enough that there are enough chance encounters of the good kind to end up with the right connections. It's essentially imagining that you release all your keys that you have in your hand in front of your door, and they're flying around randomly, and the one that opens the door magically ends up in the lock and then unlocks it. You have to do that yourself, deterministically. You go through all your keys, you pick the right one, you have to stick it in there. And the good news is that you control those processes so you always know what the outcome is going to be. If you do this on the nanoscale, you have to rely on the selectivity of that process to actually have that right key end up in the lock and unlock the door for you.
Right, and one of the challenges with getting that to happen is the interaction specificity, right? So we have a key. It has little, I don't know what you call them on a key, but the little jagged part that fits in a lock, and the lock has the complementary jagged parts effectively. But at the and at the molecular scale, I should say, we have directionality with bonds. But the nanoscale is kind of weird. It's kind of intermediate. Can you talk about that for a second?
Yeah, I think the other extreme to talk about, in addition to the keys on a macro scale, would be something like a protein and an enzyme, for example, right? Where two molecules will fit together in a very specific, well-defined way. And again, things move fast enough that those, even though it's very specific, that they randomly explore the configurations quickly enough that will happen. And that's why enzymes can do their job. That's how life can propagate by DNA amplification in your body. Crazy processes if you think about it. But it's by design in such a way that you explore all these specific configurations fast enough that you can end up with the right one that leads to success. The nanoscale is sort of in between. things are not deterministic and they don't move quite as fast as they do at a molecular level. So you really have to choose your interactions a lot more carefully. And if you're not doing that carefully, you'll get stuck in the wrong situation.
And it's also hard to engineer those interactions.
It's
right?
extremely difficult.
Right. You can leverage the directionality of atoms and their bonds at the molecular level. At the nanoscale, at least where we are today, you have much more isotropic interactions without as much directionality.
Yes, that's absolutely true.
And the one other big challenge at the nanoscale is that things like to stick to each other.
Oh, yeah. I mean, van der Waals forces make things generally very hard. And because when two materials of the same kind come together, in almost any environment, unless you have specifically matched the refractive index of the suspending fluid with the particles, they will automatically stick together. And when you talk about the nanoscale, the contact area relative to the size of the object is usually good enough that that is an irreversible process. When you put your two coffee cups in your cupboard together, they have van der Waals forces, but the range of interaction and the contact area is so small that you don't have to worry about one coffee mug sticking to another one when you want to take it out the next time.
Well, it's small relative to the volume.
Just relative to the volume and the forces that work on it on a macroscopic scale. But with nanoparticles, that becomes a problem almost instantaneously. When you have, for example, even nanoscopic spherical particles that are in a suspension, they sediment over time. Even gravity in bad scenarios can pull them together strong enough that with the best will of the world, you will not be able to break those apart very easily anymore. So you have to fight that when you work with nanoparticles.
And you mean particles in the general sense?
Yeah. Any object on that size.
Right. So where have we come so far? So we've talked about integrated versus modular manufacturing, the fact that chemicals manufacturing is very modular, and now we've talked a little bit about what makes dealing with nanoparts challenging. And so now we're going to kind of put this together and talk about a few of the things we see as being really important for the future of nanomanufacturing. And when you're listening to this, think about the kinds of scientific studies that would need to be done and pursued to overcome some of these challenges. So one of the first things we talk about, and actually maybe I'll say that what all of them are, and we'll talk about a few of them. So we defined 4 key process design needs in this article. One was the selection and optimization of what we called process breakpoints. Another was synthesis techniques appropriate for large-scale manufacturing. The third was new structure and property-based separations. And the final one, which we might leave off in our discussion, is advances in nanopart stabilization and packaging. So from my perspective, the middle 2 are the most fundamental, but the other 2 are also important. So let's talk about selecting and optimizing process breakpoints and what we mean by that.
Yeah. Before we go there, I think it's important to point out is that obviously material science over the last decades has made enormous progress, right? Why we're even talking about nanomanufacturing is that people have been able to do in a scientific setting, in a lab setting, amazing things. Things like molecular motors have been developed synthetically, so people can do amazing things. The question is, how can you do things in an environment that would make a difference in everyday life, large scale, cost effectively? And that is why we've brought up those 4 points. So we're not saying that people are not able to make things, but the question is, how can you do it in such a way that it would ultimately become viable to do it at a large scale? And that is, I think, where a lot of science and engineering has a bit of a disconnect, and that's how we ended up talking about these key steps, trying to educate both the scientists on the one end and the engineers on the other side about what is needed to make this happen. How do we bring the paper manufacturer, someone who's really good at cost effectiveness and evaluation, or a chemical engineer working in a refinery, together with someone who can make amazing stuff on the picogram scale in their lab, to bridge something in the middle that would really change our life technologically.
I completely agree, and that's a great point. In general, things to remember about this is we want to build this bridge between nanoscientists and nanomanufacturers effectively in the development of nanomanufacturing. I think we have to also assume that what's been done at small scale in the lab, while impressive and unprecedented in many cases, is probably going to be done differently when it's ultimately scaled.
Yeah, some of these processes do not translate, and that's why these core principles that we've talked about are going to be important in evaluating lab-based techniques and say, like, well, maybe this will never lead to success because it has some fundamental limitations in terms of synthesis or separations, and you're just not going to fix it. There's certain things where nature will just not give you enough wiggle room, even though it almost works. Right. You can never make the jump from 50% to 100%, no matter what you try.
Right. And it's worth keeping these things in mind as you try and develop processes. Because I think we're still at the nascent stage of nanomanufacturing. You know, a lot of people have tried, but this is kind of Gen 1 where we are today. We have a few successful things, like carbon nanotube-based materials, which we didn't talk about yet, but most things are still to come, in my opinion. And just like any new technology, like wireless communications, cell phones, it took a few generations before it really became mainstream. And I think we're working our way there, but we're certainly not there yet. So let's talk about process breakpoints. Why do you need to think about this?
Well, go back to the car example again. I think it's a good one. You want to end up with a car. You start with raw materials like latex, rubber, metal, ore even. And you ask yourself the question, how often do I want to hand off an intermediate product to the next level? If I do it too often, it becomes unwieldy and it becomes difficult to make an economically viable product if I have to ship it after every little step. If I don't do it often enough, if I don't have enough of those steps, I run into the same challenges that I already have with the integrated manufacturing. If the same manufacturer that gets the metal sheet in on the one end wants to produce a complete engine as the final product, you lose those benefits of the modular manufacturing again. So you have to carefully optimize what is reasonable. And I think, again, chemical manufacturing is a good example. When you think about specialty chemicals manufacturers, which have a very large library of modular products that they want to sell you, they don't have an infinite library. And there is an optimization, depending on the process that they have, is what is their number of products that they want to offer to the next level. And that depends a little bit on the product, but you have to really think about it. And you have to think about why one point in the process may be better as a break point than another. You have to allow, for example, for the handoff to take place. If a modular material can only survive in complete oxygen-free environment for a day, that's not a good step to hand it off to the next step of manufacturing because it's hard to maintain those conditions. So you have to really carefully pick your break points.
One of the examples we gave in the article was kind of comparing and contrasting zero-dimensional nano crystals, nano dots, particles, and nanowires. So not all applications are like this, but if you have an application where you want to have basically a one-dimensional rod of a certain doping concentration, and you may want this in a thermoelectric device, you could start with 0D particles, and people have done really beautiful work, DNA assembly, other kinds of assemblies where they take these dots and they string them along to form a line. And then you can imagine, okay, let me sinter those together to get the rod I'm looking for. But if you start with that kind of level of modularity, you have to coax them into a line, try and prevent them from branching, which they often like to do. And then if they branch, how do you purify the branch ones from the straight ones? And do you even want those interfaces between the neighboring particles, or do you want a nice crystal? And I'm not intending to make nanowires look really good here. I'm just trying to point out that there are different types of synthetic processes and types of nanoparts that you'll want to choose in different applications. And I think we probably do too much worrying about dimensionality for no particular reason, when we should mostly be guided by what are we trying to make and what are the properties and structural details that are required to make that.
And you also have to think about what ultimately the flexibility is that you want to get. For example, polymers are a great example of that, right? Think about your monomers as your quantum dot and your polymer as your nanowire. In some cases, we really want to have this very controlled sequence along the polymer. We want to make AB, AB, AB copolymers. And having A and B be available as modular materials, monomers that you buy, and then the polymer manufacturer takes those monomers and strings them together in a controlled way, may be a good idea, especially if the next time I don't want A, B, A, B, A, B, but I want A, A, B, A, A, B, A, A, B.
Right.
The polymer manufacturer wants to have the raw materials as modules available because they can now modify their process and make these subtle changes themselves. If they buy the A, B, A, B, A, B from someone as a module, they're hosed because they can't make the A, A, B, A, A, B anymore. And that's the other part of this decision making about where do you have breakpoints. You want to optimize what you may want to do in the future in terms of alternative development, and that's why you have specialty chemical manufacturers that sell you certain products but not others. They don't go too far down the line in synthesizing really complicated structures because they know you want that flexibility yourself. So it's up to you then to generate the next level.
Right. I'm going to touch on a few things that are also in this section because I think they're worth mentioning. I kind of just touched on interface management, where you may want no interfaces, a perfect crystal. There's other times where you want flexibility and you're okay with interfaces. And you just have to figure out which you need and pick the right synthetic technique to get you there, right? Oftentimes, if we're talking about assembly of things, multifunctionality is really important, right? I think the example we give in the article is back to the car is the alternator, right? The alternator also has other pieces attached to it that go beyond its function that's in its name to attach it to the frame of the car, for example, right? And in terms of building nanoparts, we're not really good yet at having functionality plus components on the part, the object, that drive its assembly. Right? We can often do one or the other, and most times not both. So that's something. When you start to assemble these things, and this is something I was first made aware of by John Main at DARPA with his Atoms to Products program, which I'm not a part of, but I think he very rightly pointed out what happens when you take nanoparts and start to assemble nanoparts to build microparts and assemble microparts to build macroparts. Things change as you jump length scales. And so this goes back to how do you divide the process up? And you need to be careful because the physicochemistry of parts, as we were talking about earlier, changes at these different length scales.
I totally agree with that. I mean, if you think about, again, making a wire out of spheres, if every time you touch a sphere to another sphere, you incur a large electrical resistance, for example, and electronic functionality is important, then that may not be the right way to go. You may actually have to really develop your rod without that problem to begin with. And that depends on final application. In some cases, making a rod out of spheres may be perfectly fine. In others, it really is not worth it. And that's where, again, molecular scale and macro scale and nanoscale are fundamentally different from each other. When I tie a polymer together from monomers, I know that they have a covalent bond everywhere and they're pretty well defined. If I macroscopically put two objects together, I pretty much know what the contact is between them and can control it. The nanoscale is subtle enough that what you thought was going to be great actually ends up not being all that great, and it can really ruin the functionality of an assembly.
Right. Real quick, back to this point on hierarchical assembly, because I think this gets missed a lot. If you take a 1 nanometer cubed, for lack of a better size for now, 1 nanometer cubed nanopart, and you start assembling these 1 nanometer cubed parts, the first part you add, you double the volume, right? But as you keep adding that same size nanopart, the increase in volume you get goes down tremendously. And eventually, you're not really adding any volume by adding one more 1 nanometer cubed part. And so what you have to then do is take what may be a 100 nanometer or 1 micron on a side part and assemble it with another 1 micron on a side part. And what's the interfaces when you assemble those together, right? These are some of the things we point out, and there's just tremendously rich science that can be done in this space. And so we're excited about it, but we just think there's all sorts of challenges, which I guess is what gets scientists and engineers excited. So let's go into the next category of things we laid out, and that was synthesis techniques appropriate for large-scale manufacturing. So we lay out a few things, and this is mostly to make people realize that what's done in the semiconductor industry is unlikely to scale to the kind of large-scale nanomanufacturing world. The first one is 2D versus 3D. So if you're growing nanowires and you want to grow nanowires off of a surface, you can do that. And then if you want to grow more nanowires, you can make the surface bigger, right? But you can only make it bigger so quickly. What you really want, instead of just 2 dimensions with which to scale material, you want the 3rd dimension. And you want to then grow nanowires, for example, in the bulk.
Yeah, we've done this with office space, right? You want to have a certain productivity, so you can't scale in the flat plane to put more cubicles together, so you grow these tall towers where you can stack cubicles vertically, right? It's essentially a reactor optimization problem. How can I use my space effectively to generate product? And if I can, in a large volume, take advantage of every volume element in there to give me productivity, then I can get a lot more done than when I can only use the walls of that reactor. It's not favorable. And that people underestimate how big that effect is. That if you talk about volume, productive capability per unit volume, that's why chemical engineers like to use large pieces of equipment. That's exactly this scaling phenomena. And a lot of nanoscale manufacturing in the lab does not use it because it's complicated and it's a fundamental scale-up process.
While you're talking about that, it's worth mentioning that we don't love dealing with large volumes. There's all sorts of other challenges when you have a reactor that's a meter across. There's challenges in transporting material. There's challenges in heating material. And so that's why they pay the chemical engineers the big bucks. At least I tell my students that. And there's emerging ways that people are thinking about overcoming or kind of sidestepping those challenges. But we do it, as Victor was saying, because of the 3-dimensionality.
And it's a use impact, right? I mean, if you just think of a cubic meter versus 1 liter, right? All things that you can easily imagine in your scale of your office. It's like, oh, what's the difference, right? A cubic meter, 1 meter by 1 meter by 1 meter versus a liter, the bottle that you have on your desk. Well, you need 1,000 of those bottles to have the exact same productivity that the cubic meter does. So there's a clear payoff there. I can try to assemble 1,000 reactors of the size of the water bottle, or I can build 1 reactor that's a cubic meter and get the same inherent production volume. That's why people worry about making these larger reactors, because the scaling is kind of insane.
And that's how we've done it, and we're going to continue to do this for a long time. However, advances in automation and other kinds of sensors and things in the last couple decades have made making 1,000 individual 1-liter reactors more feasible. I'm not saying they're going to be feasible in all situations, but there is a lot of interest in this right now, so it's worth mentioning. And going back to my nanowire example for a second, I would be remiss if I didn't point out the beautiful work at Lund University using their technique they developed called aerotaxy, where they take nanowires and instead of putting the little seed particle that choreographs synthesis on a substrate, which is how the majority of the community does it, they entrain it in the flow of a reactor. And then the wires kind of get spit out as they're flying down this tubular reactor. And it's very akin, if you know how carbon nanotubes are manufactured. We won't get into the challenges of doing it with nanowires versus carbon nanotubes, but that's exactly the kind of thing we're talking about, where they can now take advantage of the volume of the reactor versus being stuck on a surface.
And I think the number of those processes that have really tried to more or less successfully do this tells you how complicated it is and how challenging it is, right? There are probably 1,000 scientists doing it on the surface for every scientist who really tries to do it in volumetric bulk flow. It's the 1-liter bottle versus the cubic meter. And it's really non-trivial. But ultimately, to do it in a scale that matters, it's likely that the volumetric approach is necessary.
And in terms of the science, it's not that we're going to build a 1-meter cubed reactor. I mean, a 1 liter or even smaller will tell you a lot, and you can study the process. But the process itself has to be amenable and suitable for these volumetric, to be done volumetrically versus aerially, right? So that's the point here. It's not that we're advocating for a bunch of 1 meter cubed reactors to be installed across the country, but you have to think about how you're processing things at a fundamental level. Another one of my things is condensed phase versus gas phase. And so people have done really beautiful things in condensed phase. Colloidal synthesis, it's often referred to, or hydrothermal synthesis. And really tremendous functionality and shape control and property control has come out of this work. And the quantum dots we were talking about earlier that are in TVs are done this way. What I want to say, though, is I really dislike when I see an introduction of a manuscript that makes a very glib statement like, well, because it's done in a beaker in a hood, it's inherently scalable. And that just shows basically an ignorance of how we do things at large scale. If you were to look at the top 10, let's say, largest scale produced chemicals in the world, the large majority of them are done in the gas phase. Right, and so it's not that liquid phase is not valuable at all. We've made tremendous things and will continue to be a really critical piece of nanoscience and nanomanufacturing. It's just that that's not the only way to do things, and that gas offers you a lot of benefits as well, and that scalability doesn't strictly come from temperature and materials of reactor construction.
One key element here is coming back to this stochastic nature of processes, right? That in a gas phase, everything moves so much faster, so much more easily that you get 3 orders of magnitude, at least generally, in rates at which things move around. So if you think about the number of configurations you need to explore, you gain a tremendous number of configurations you can explore in the gas phase relative to the condensed phase. And if that becomes a critical step in this, that you have your keys randomly flying around and they need to find the right configuration, if you can increase the likelihood of that happening by a factor 1,000, that makes a big difference in terms of success rate of your process and economic viability ultimately.
Right. So the last thing let's talk about in this section, because it leads into the next section, is that different reactors behave differently. And this is something that's basically undergraduate course content for chemical engineers, but it's worth mentioning that depending on whether in the two normal kinds of reactors are tubes or stirred tanks, and the stirred tank is exactly like your blender at home, and a tube is literally a tube where reactant goes in one side and products come out the other side, they behave very differently in terms of how they mix reactants and how long different fluid elements stay in the reactor. And that leads, in the nanomanufacturing context, to very different details in the product parts. So maybe you want to talk about that a bit, Victor?
Well, I'm an applied physicist, we said, right?
Okay.
This is much closer to your area of expertise, because the difference that you see here, I think for someone who's not a trained chemical engineer, seems kind of trivial, but once you're a chemical engineer, you understand that your full understanding of that difference is actually what makes you a chemical engineer. That the way you put reactants together and you mix them and you take product out and you keep feeding reactants in has a tremendous impact on the kind of the outcome of your process, the quality of your product. It's really hard for a non-chemical engineer to appreciate that because they haven't thought about it enough. And we fill an entire course with it, essentially, right?
We do, and it's not something that we're going to be doing fundamental research on anytime soon. But again, it's worth realizing that when these things get scaled, this is going to be an issue, and you will have products of nanoparts where there's going to be a distribution in structure. So take the quantum dot example. You might have a distribution in the size of the quantum dots. Some dots spent longer in the reactor than other dots, and so you have that kind of distribution, which in the case of a quantum dot, its size or its diameter will dictate its properties, and that becomes a real problem. So it's not just a distribution of structure, it's now a distribution of properties. The last real thing I want to touch on is this idea of structure and property-based separations, and we'll wrap there. We do it, as we said a second ago, when we process chemicals, because we get distributions of products, and there's nothing we can do. Well, we can't always get rid of that distribution. And so we have to assume there will be variations in structure and properties of the resulting chemicals. And as you can see from what we were just talking about, due to reactor design, you can get differences in the structure and properties of quantum dots or other nanoparts. And so we feel that this is an absolutely underappreciated area and certainly understudied area, and that's going to be separation of nanoparts.
Yeah, and I think this has been recognized by some parts of the community investigating this. NIST, for example, National Institute for Standards and Technology, I think it's right. They have understood that when you have all these nanowires, that you can't just separate them by length or diameter, but you really have to realize that the way they're created creates differences in electrical properties, even if they have the exact same length and diameter. So you need a different kind of separation, potentially.
Are you thinking about carbon nanotubes?
Carbon nanotubes.
Okay.
And it's a very difficult problem, right? Because how do you separate things that look exactly the same and just have a different color, essentially?
Right, and if you're interested in this, I'll just throw this out there now. Mark Hersom from Northwestern was on the podcast about a year and a half ago, and we talked about his work in separating carbon nanotubes, and we touched on some of these things in detail. He's done work on CNTs as the NIST team has done, and they take different approaches to separate carbon nanotubes, and there's pros and cons to both of their approaches. But the idea that you need to separate a carbon nanotube that has the same diameter and length from its neighbor, but their chirality, the way they're twisted, is subtly different, and thus gives them different properties, is really important.
And this also feeds back into the earlier discussion about breakpoints in your process, right?
Right.
Because typically you would generate different grades of a material, different levels of purity that you would then pass off to the next step in the manufacturing chain. And you would pick a point where you can make those separations, where you can actually say, oh, this is my product, and I can spend a lot of energy and time to try and make it as pure as possible, or I give you a cheaper grade of it, and for your product, that's perfectly viable. If you buy a gas tank from a gas manufacturer, you can get it with 99.9999 purity or with 99.9.
Right.
And you buy the grade that you need, but you need to have the fundamental process in place to even allow you to have that flexibility to go from 99.9 to 99.999.
One of the examples we have in the article is we compare what you might need if you were separating nanocrystals of different carrier density. So this is the number of carriers per nanocrystal, charge carriers, electrons or holes, depending on the kind of nanocrystal. And we compare it to uranium separations, right? People think of uranium, the separation of U-238, the abundant isotope, from U-235, which is what we use for fission. And the mass difference there between those two is 1%. And that's a heavy-duty separation. It's when you use centrifuges, you're using many centrifuges, each one giving you a little bit more separation than the previous one to get those two separated. Now, if you look at the nanocrystal case, if it's, let's say, silicon, one phosphorus atom in a silicon nanocrystal versus its neighboring nanocrystal, which maybe has two phosphorus atoms, is kind of a mass difference on the order of 10 to the minus 4. So that's 5 orders of magnitude less mass difference than the uranium example, right? And a 2x difference in carriers could be very significant in the way a device performs. Or if you have a distribution of carriers, maybe you have an ensemble and some have 1, 2, 3, 4, now your collection of nanocrystals that a current is passing through gives you properties that are not great for your application. So this is a great example, I think, of the kinds of problems and challenges, and I think there's a lot of science to be thought about of how you would do that. How would you get all nanocrystals with all one phosphorus atom? And to go even a step further, we know from some really nice work that where the phosphorus atom sits in the nanocrystal really matters. If it's in the core versus closer to the surface, it can behave differently. And so how do you get all nanocrystals with all the phosphorus atoms in the same place? Or on the flip side, how do you design a process that, or a product, a device that is able to tolerate those variations, right? These are all really interesting scientific questions.
And I think the separation side of this has been very underappreciated. And as a result, people just focus on, I'm just going to make everything in a perfect way.
Right.
And you know from other practical examples that on scale up, that is just not going to be the winning model, right? I mean, even for cars, they test cars at the end of the line, and occasionally there's just a dud, and they will say, like, okay, it's we're not gonna ship this to the next level.
Well, people miss that embedded in that car are all the modular parts that had been separated earlier.
Yep.
And that's a big deal.
But you have to have the tools to even investigate the property and even measure the property that you then want to select for. So these separation processes are complicated, and currently the only way around it is, if you don't want to think about separation, is that you have to make the perfect product to begin with, or you just accept that whatever you have is what you're going to have to live with. And I think adding separations to your arsenal of techniques, a range of separation techniques, allows you to be a little bit sloppier in your synthesis, or if you have a not so great product, to upgrade what you can use the product for by using the different separation techniques. And that's what a refinery works on, because they end up with a very sloppy kind of product in the catalytic cracking of a vat of crude oil. And then they have these dedicated separation processes that allows you then to separate gasoline from kerosene, from other valuable products that you want to use. So having flexibility in your production process where you can compensate for some of your sloppiness in your process through separations, or where you can upgrade your product by applying separations after the fact, that's what makes it a full, flexible manufacturing process.
And I think it's worth mentioning, we call them separations and not purification, because we want to use everything we separate. To have a process that's economically viable, you can't throw out a bunch of stuff. You have to sell as much of what you make as possible. So designing the synthesis and designing the separation so that the products, once they're separated, can all be sold like we do in petroleum refining is really important. And the last statistic, last thing I'll leave you all with is that we spend 15% of worldwide energy on separations. So it's tremendous. We don't recognize it, but they're all over the place. In the chemicals industry, in other industries, pretty much all industries, except for the electronics industry, as far as I can tell, in terms of chip manufacturing, we separate and sort or purify, and different industries call it something slightly different and do it slightly differently. But this idea that you're never going to be perfect is probably something we should take to heart in the nanomanufacturing space. I said in the beginning I wanted to touch on your role as associate chair for undergraduate studies. Can you talk real quick about what that is and what you do?
Well, it's kind of like parenting 1,000 students at the same time, right? So in terms of the undergraduate program, making big picture decisions about what should and should not be included in the curriculum, and how do you train students to be successful in their life afterwards, but also really individual mentoring, an environment in which individual students can optimize their academic and professional success once they leave Georgia Tech. It's been an interesting environment. So it really at times feels like parenting 1,000 students.
So you just came into this position this past summer, and you also end up having to manage the faculty. So it's not just the students who you have to parent, but you sometimes have to parent the faculty, and you're trying to deploy the faculty as best you can in the classroom and as mentors to individual students as well.
Yeah, I will not comment on how difficult it is to guide 40 colleagues versus 1,000 students, but they're not on completely different orders of magnitude.
In terms of the challenge, one of the things I tell students when I'm kind of telling them you should talk with faculty more, I said, one thing, though, is you have to recognize that if you ask 3 faculty a question, you get 9 answers. So just be prepared for that.
Yes, and I have to deal with 9 answers from 3 of my colleagues. And for students, it's not quite that complicated.
Right, exactly. So with that, Victor Breedveld, thank you so much for coming on the podcast.
It was a pleasure being here.
You've been listening to Nanovation. If you enjoyed the show, please leave a rating or write a review on Apple Podcasts. Show notes are available at fillerlab.com/nanovation. Nanovation is recorded in the Marcus Nanotechnology building on the campus of Georgia Tech. Andrew Cannon edits the show. I'm Mike Filler. See you next time. Did you go running this morning?
No, I actually didn't. I finally went running yesterday after about a week, and I was hurting this morning.
Okay. Now
I am not in shape for the Pi Mile.
I'm in shock because I assume you run pretty much every day, and you had for a long time, right?
Since Sylvie was born,
Yeah.
I've actually she wrecked my running. She literally wrecked my running.
The second child.
The first child was helpful. I actually ran my PR on the 5K a few months after Iris was born. Sylvie just screwed everything up.
I'm not sure it's Sylvie's fault. I think it's, and a lot of parents would say the second child just bowls you over.
I was amazed at how big the impact was.
Yeah. I think I've always described it to scientists and engineers as your kids will always have a phase shift relative to each other in terms of what they do. So when you have one kid, the kid can nap and you can do something else, or you can relax and take a break. When you have 2 kids, they're unlikely to take a nap at the same time, even if you're trying. And so one kid takes a nap, the other kid is up, and you're paying attention to them or making sure they don't hurt themselves. Then the kid who's sleeping gets up, the second kid takes a nap. And so it's just this constant need for attention from one of the children, and that just gets tiring.
And even worse, in the mornings, just get everybody ready on time. Since Heather has to leave at the same time that I do, you need 2 people to keep them both under control.
And then you think, I'm thankful I'm not a single parent.
I don't know how people do that.
Yeah.
I was by myself for 9 days when Heather recently was in Iceland. And I made it work. But long term, I don't know how you would do it.
Yeah. No, I really don't know, and my hat is off to people who are in that situation and are able to manage it.
Or more than 2, right?
Right. But you would say once you get to 3 or 4, the older ones parent the younger ones. Okay, I don't have more than 2, so I really shouldn't pretend to understand that I know what it's like to parent 3 or 4. But okay.